Hello and welcome. This is tutorial number 6. This is again almost where we left off last time. There are some tiny changes I've made to the level data. I linked each patrol point with an unnamed link from the area. Points 1, 2, 3, 4. Then I added the name patrol point to the property Warhorse AI entity category of each point. And I also linked the NPC1 with a link named guard. I will explain the purpose of these changes later. So, today we won't care about the random patrol part at all, so move it a bit to the side. Just select the group and Ctrl-Shift-Click. We will do some changes to the patrol part. The NPC1 will continue doing the patrol, but the patrol points will be all placed inside this smart area. When the player enters the area, the NPC will react. So we will finally give the SmartArea a SmartArea type brain and take advantage of its inherent properties. Also, we will start using messages. And finally, we will have to modify the patrol behavior itself. First, it will have to be able to receive the messages. Second, it will introduce two modes. The first mode will be the standard patrolling, and the second one will be some reaction script to the intrusion when the player enters the area. Let's finish the level changes first. Spread the patrol points so that they are at least some 10 meters apart. You can use this ruler tool here to measure distances. So now this distance is some 11 meters and diagonally it's almost 16. Make the shape more squarish. Fine. Now we have to reshape the area. Just click the Edit Shape and move the area points. Click again, and now you can see that all the patrol points are inside the area. I will also hide the links. They are becoming a bit too distracting. Now rebuild the nav mesh and save the level. That's all for the level edits. Now we have to create a brain for the area. So let's go back to the XGen NPC editor. Go to the Brain tab and create a new brain, test STSA. Then add a new subbrain to it. It will have the same name, it will be of the type SmartArea, and the implementation will be stored in the same file where we already have the area's behaviors. When we were creating the NPC subbrain, that was the type behavior tree, there was only the onUpdate available. SmartArea can have all these options here. Check them all. OnUpdate is a standard tree, and just like in the NPC, it works all the time and restarts itself when it's finished. These other trees are executed only on certain events. Their functionality is quite self-evident. OnRequest is executed only when somebody calls a behavior from the area. OnRelease is executed when that behavior is finished or released. OnEnter is executed when somebody enters the area or starts inside of it, and OnLeave is executed when somebody leaves, of course. OnEnter and OnLeave can only be used on smart areas. That is the main difference between smart areas and smart objects. In the Smart Area tab, click here to select the brain for this area. Oh, and I forgot to save the brain, so save it then save the SmartArea, and then reload the AI scripts. When I reselect the area, we should see the proper brain and subbrain. Yes, you can see the new name right here. And here you can switch between the 5 different trees of this subbrain. Their current form would unfortunately result in fail spam because they are completely empty. We will only care about the on-entered tree today, so we have to prevent the failures in other trees. We will put on update to eternal sleep by plugging in wait -1. The other trees will need instant successes. So the on-enter. I will just copy some prepared tree from here. Whenever we enter, we want to use this script. First, we ask if the entity who entered is the player. You simply compare player to the automatically generated variable _bodyinfo, which holds the data about the entity which caused this tree to be executed. Unfortunately, bodyinfo is not offered in autocomplete, so don't forget it exists. Anyway, if the bodyinfo ID is equal to player, then in the next step we find the guard NPC using the guard link. That's why I added the link here. There are more ways to find him, but this solution is simple and easily understood. So we find him and store him in the new variable guard of type _wait. And then we want to send him a message. So now I have to explain messages. Message system provides you with tools to send any data to any entity with a brain. You can use any existing data type, but messages very often use custom compound types, which is the reason why there is so many of them in the type definitions file. Well, one of the reasons. Whoever is meant to receive the message must have a mailbox which is set up to accept that type of data. If you send a message to someone who cannot receive it, the send message node, like this one, will fail. There's over a dozen different message nodes, but the main ones are these. Send message sends the message and waits until the message is processed. Then it succeeds. Instant send message is different in that it doesn't care about the processing. It's basically fire and forget type of the previous node. Multi-send message, which also comes in the instant form, can send the same message to an array of entities. And then on the other end, you have to catch the messages. So we mostly use read message and process message. Read message waits until there is a message to read, then it succeeds. Process message reads the message. As a reaction to that, it also executes its subtree, like this success, and it can send some answer data back to whoever sent that message. Then it succeeds. So we will use the instant send message. We only have one recipient, and we don't care how he deals with the message, so we can fire and forget. Let's set it up. I have this new custom type defined here in type definitions. It's the type test_st with subtype intruder. The subtype has a member also called intruder of type _wait, because we want to send the data about whoever entered. This will be a new type definition for you, so don't forget to restart your editor. You can enter the message data in the send message node in two ways. You can create a variable and set up its values, and then you simply send the variable. That's this field. The guard variable is not of proper type, but this is how you would use it. Or you can avoid the variable and send the data directly. You simply state the data type and then list the members with their values. We will use this second approach, these BB fields. Enter the message type. I already have it prepared here, so I will just copy it. Unfortunately, there is no autocomplete for this, so mind the typos. Then enter the single member in the field values. Again, no autocomplete for member names. Sorry. The value can be player or body info ID. It's the same value in this case because of the if condition. But if we wanted to pass along the data about anybody who enters, we would have to use body info ID. Also, don't forget the $sign here because we need to refer to a value stored in a variable. The target, that's the message recipient, will be the guard. And that's the onEnter tree finished. Now we have to define a mailbox template so that the MPC can receive the message. Click up here on Mailboxes, Edit Templates, and you're in the Mailbox editor. In this window, everything is done using context menus. So right-click and select Add Mailbox. Give it the name intruder_st and leave everything else in default, that is time limit -1 and onAccept set to consume. Use the filter here to find it because we also have to add the type it can receive. Right-click on the mailbox and select Add Accepted Type. Unfortunately, this window doesn't feature any autocomplete, so beware of typos. Type in test_st intruder. So that's the mailbox template defined, and now let's finally address the patrol behavior. This is still the same behavior we created in the previous tutorials. If I jump in, nothing should change here. Let's see. F9 and select the areas on Enter Tree. You should see that the area is already attempting to send the messages to the guard every time you cross the area boundary. The NPC doesn't react to anything because he still doesn't receive, let alone read and process, the messages. But the area is working fine. So, back to the behavior. Let's add the mailbox. This is done here in the Inboxes section. Just add the mailbox we've created. When the NPC is in this behavior, it can now receive messages of the type this mailbox can accept. And you might be asking, but Mr. Warhorse developer, can I accept these messages before this behavior is called? Good question. No, you cannot. This mailbox is added dynamically to the list of NPC's inboxes once the behavior is called, and it's removed when the behavior is released. And you might be asking still, but Mr. Warhorse developer, what if I have 2 or more trees with the same mailbox included at the same time in different parts of the subbrain? Or if I have multiple nodes reading from the same mailbox? Basically, you have one read message here and an identical one here, and you send one message. Will each inbox receive a copy of the single message when it's sent here? The answer is yes. It doesn't matter how many identical mailboxes or different mailboxes with identical accepted type, or how many identical read message nodes you have in the entire brain. Each will process its own copy of the single message. If you want to distinguish different read message nodes reading from the same mailbox, you can utilize the condition field or if condition nodes to filter out whatever you don't care about. And finally, you can also add an inbox on the brain level. In that case, the NPC can receive such messages at any time. So, the behavior tree. We will change this old behavior into this. And you might have gotten a bit scared right now by this behemoth. Well, it gets less scary when you look at the same version divided into topical segments. The main gist is that we want the behavior to feature 2 exclusive modes. The NPC is either on patrol or it is reacting to our intrusion. So this purple part is the patrolling, the green part is inspecting, and this part takes care of proper switching between the two modes. And here at the very root is a parallel. So independently of this whole rest of the script, we are receiving messages about the intruder. Let's dive into details. So I added a variable mode of type string with the default value set to patrolling. Here we are waiting for the messages in a loop. Let's set it up. We must enter the inbox name from here. Again, no autocomplete. And then we must specify a variable where we store the received data. So create a new variable, message data, of type test_st_intruder. And then insert it here. Also, in over 90% of cases, you want to process the messages atomically. So, when we receive a message, we ask if the current mode is patrolling. If so, we set the mode to inspecting. Then the loop repeats and we are waiting for another message. So the other parallel branch is the rest of the behavior. We already established that these are the two different modes, patrolling and inspecting. And they are preceded by this mode switching logic, which utilizes a node called continuous switch. Continuous switch is derived from a standard switch you can find in C or plethora of other languages. And finally, you can also use it in this system. The simple switch looks like this. A switch only accepts if condition nodes as its children, and then it tests them one by one, and the first one that is true will get executed. Continuous switch adds a twist to that. It keeps checking the conditions with every AI tick. And if the condition stops being true, the subtree of that condition is so-called killed from above, which means that the subtree fails. The fail state is propagated upwards, and then it's consumed by the continuous switch, which means that it's not propagated any further. If another condition is true, then its subtree will start being executed instead. If no condition is true, then the continuous switch node fails. So continuous switches are usually used in cases just like this one, where we need to swiftly switch between different subtrees and we know they are mutually exclusive. Let's look at the flow from the start. I will just plug the root to this new version. So, we start. The mode is set to patrolling, and no message has come yet. This gets to the continuous switch. This first condition is true, and we are in the patrol. When we receive the message, we set the mode to inspecting. This tree, wherever we are in it, will fail. The fail will, so-called, bubble up until it gets here. And then this part opens. That's a sequence, so we go like this sequentially until we get here. The patrolling is simply this old behavior plugged under the if condition. There's really nothing new to see here. So, how does the inspecting part work? It starts rather simply. We reset the speed. It's a variable of type string with default value set to walk. Then we use distance condition to test if the player is far. This is basically the distance gate node, which you already know, in a non-gate form. So, if the player is farther than 10 meters, we set the speed to run. Then we move to the player's position at the time of intrusion. The destination is the entity received in the message. We are using the proper speed and we stop within 2 meters distance. What should the NPC do next depends on whether the player is far or close when the NPC finishes moving. If the player is far, the NPC will play an animation of looking around so that it looks like the NPC can't identify the intruder. If the player is close, the NPC will play a different animation and then it will keep turning towards the player as though he's waiting for him to leave. So how do we do that? I'm using a selector node here. There are more elegant ways to do this, but I want to show you its function. It's a very useful node. Selector has several child trees, and its goal is to eventually find the first one that succeeds. It does so by attempting to execute the child trees one after another. If a child tree, like this part, succeeds, the whole selector succeeds, and then the script continues, which means that due to this sequence, we would go down here. If a child tree fails, then the fail is consumed by the selector and it tries the next child tree. And if that one succeeds, the whole selector succeeds as well. So here in the first child, we test if the player is closer than 5 meters. If he is close, we use the fail node, which obviously produces a fail. As a result, the rest of this subtree is ignored. So this fails, this fails, this fails, and then the selector consumes the fail state and opens this logic, which is dedicated to handling the player is near situation. If the player is farther than 5 meters, the distance condition doesn't fail and it will go right here. In this part labeled far, we play animation called looking around. Some more information about animations is needed here. There are 2 types of animations. Looped animations are endless and you have to terminate them after some time. One-shot animations have a predefined length, so they end themselves. You can tell them apart in the mannequin tool. Let's look at looking around. When this strip goes forever, which is the case here, it's a looped animation. This is the other animation we will be using. Here you can see the strip ends at circa 2 seconds timestamp. So this is clearly a one-shot animation. I also have to explain in more detail how the play animation actually works. When the move node is executed, the node starts, then the NPC moves, and then the NPC reaches the destination. Only then the move node ends and the script continues. Play animation is different. When it starts, the NPC starts playing the animation. Well, more precisely, the animation gets queued. The animation can be interrupted either by movement or by some other animation-driven node like picking items, or by explicit termination using stop animation node. The important point here is that the script continues right after the play animation gets started. That's why this timer is here. It ends this part after 8 seconds. So this succeeds. Then we do some operations here, and then we go back to patrolling, and this move node is the actual thing that ends this animation. Now let's inspect what we do when the player is close. When the player is close, we play this one-shot animation ADLG emphasis with tag angry. Then we want the NPC to keep turning to the player using turn body. That's clearly an animation-driven node, so we want to first wait for the end of this angry animation. This is done by storing the reference to the instance of this animation in a variable of type common with. This variable is called animation. And you place it here. Then you use this reference in animation end wait node, which succeeds when this animation finally ends. Then we go to this loop. In this loop we use turn body, where the NPC turns so that it faces the player. Then after 1 second, we loop it and try the turn body again. If the player has changed his position, the NPC will realign himself. And then parallel to all of this is this timeout timer set to 15 seconds. So after 15 seconds the timer succeeds. And because this parallel node is set to success mode any, it succeeds. And this part is terminated. So basically the NPC has a hardwired 15 seconds time limit to do all of this. And then he just gives up and this succeeds. This sequence takes control and we get here. This part does some preparations before switching back to patrolling. We want the NPC to continue patrolling not from the point where he was when we entered the area. We want him to find the nearest point and continue from there. For this I have an indexed array called points. First I reset it, and then using graph search I find all the patrol points. Here, for educational purposes, I'm using a different approach than what you are used to. As I said in the beginning, the points now have the entity category set to patrol point. And there is a category filter which you can use to search for entities based on this data. So this setup uses any link, we don't care about the link name, and whatever has this patrol point category is added to the array points. And as the final step, the array is sorted using this range sorter node. This simply sorts the array members by distance from the reference point, which is the NPC, obviously. Then I simply copy the point 0, which after sorting is the closest point, to the next point variable, which is used by the move node in patrolling. And then I set the mode to patrolling. This whole thing succeeds, the continuous switch registers the change, and then we go to patrolling. And that is the basic principle in the loop of this behavior, in which this whole system can work forever. Of course, this is all just a simple make-believe approximation of a real guard's behavior. The real guards in the game use way more complex systems, orders of magnitude more complex than this. And as a side note, we shouldn't even use this animation ADLG emphasis because it is intended for use only in the dialogue system. So it will have some ugly transitions, you will see. Let's finally test it. Save and jump in. So the NPC is now patrolling. Now let's enter the area somewhere near him. He walks to us. We are close, so he plays the angry animation. This is the ugly transition I told you about. Now he's turning. And after 15 seconds, he should give up and go back to patrolling. Yes, so the nearest point is clearly this one, and now he's in the loop. Now let's re-enter the area when we are far from him, and let's quickly get away. He should run, and then he should play the looking around animation for 8 seconds. Then he should go back to patrolling. Again, the nearest point is point 1. Let's just test if the nearest point logic works. Now he's angry, and he should then proceed to this point. Yes, so this works. This behavior is still a bit too simple and can be massively improved. Some examples: the NPC doesn't react to us leaving the area, and there's zero cooperation between multiple guards. Also, this time I didn't care about save and load as it would complicate this entire exercise too much, but I do recommend that you try to implement it. And I'll give you some tips for that at least. First, you want to set the mode to be persistent. Second, you also want the message data to be persistent. Third, you don't want to repeat the movement if you were already in this part. And tip number 4, you certainly want to atomize the final step. And I still may have overlooked something. So, I wish you good luck with that, and this is the end of this exercise. See you next time.